on Chapter 3, which is still kind of a review of what we did last semester. I mean, it goes into a little bit more in depth, but it's still very similar to the data mining process that we worked on last semester. So, the Introduction to Data Mining chapter focuses on the main concepts in the data mining workflow. So, in the past couple of decades, we have begun storing large quantities of data from a multitude of sources, and businesses began realizing that with all the data they were collecting, they might be able to gain an edge, and if acted on that edge, they could profit. So, the overall process of data mining is to take in data and some analysis goals and try to obtain unknown answers and insights that can be acted on to achieve those goals. Now, the key word here is unknown. The reason data scientists get paid so well is because they are typically trying to solve problems no one else has ever solved with little to no help. So, this is an image from your book. It kind of details the data mining workflow that we're going to go over throughout this semester. So, this is an example of a typical data mining workflow. We will talk about each of the boxes in this flow diagram either today or in a future live session.
Can you hold it right there? Is this, because I got the digital copy and it didn't show this chart, it shows just the arrows.
It just shows just the arrows?
Yeah, in my ebook. I didn't buy the hard copy, I got the ebook. But it just shows the black arrows, it doesn't show the square boxes. Do they go through all of these types of modelings when they're doing their data mining, or do they pick a few that they know they're going to do?
No, they pick a few that, like, as you understand the kind of data that you have, different kinds of models can be used. So, in a couple of slides, I think we talk about different data types, and depending on the data type that you're using, you might use a different algorithm. Like, we're going to talk about ordinal numbers, like Likert surveys, the typical,
okay.
Satisfied to unsatisfied, and there's usually each of those numbers means something. Well, you can do a special kind of ordinal regression as opposed to just a regular multiple regression based on the kind of data that you have. But you wouldn't do both.
Okay.
It also depends on what your goal with the analysis is. So, the first step in the process is to usually meet with key stakeholders to try to define exactly what the problem is and what are the goals of the analysis. Then we would discuss what data we would like to have in order to perform that analysis, and then what data is actually available. Very rarely will you get all the data you need or want to solve the problem. This may require some improvisation on your part to try to figure out what kinds of models might apply. You will also need to keep track of your assumptions, as many models cannot be performed if you violate those assumptions, and when you're in a meeting, that might be a question someone asks you when critiquing your analysis. Generally, you will have to do extensive background research on the problem to gain a better understanding of the problem domain. Kind of like with the healthcare project we had last semester, where I asked you guys to look in the research to see what was going on with emergency department overcrowding, so you'd have a better understanding of why we were trying to analyze the problem. So, many times we only distinguish between quantitative variables and categorical variables. But quantitative variables, also called continuous, and categorical variables are also called discrete sometimes. However, like I was just saying, certain kinds of analysis can only be done on certain kinds of data. For example, some econometric models, such as panel regression, require interval data as we need to perform regression with respect to time. Another example is the ordinal data, like I was just talking about, where you have the Likert scale data, where we use numbers 1 to 5 to assign our satisfaction on a survey. In this instance, the numbers are categorical, but the order has meaning. That's where the ordinal comes from. And finally, ratio are typical quantitative variables. And nominal variables, where we use numbers for categories, but they have no inherent meaning, such as you are in group 1 and someone else is in group 2, but the group number really has no actual value to, there's no superiority in group 1 over group 2. They're just both labels, basically. So, databases hold most of the data a company you will work with. MySQL or Microsoft SQL Server or SQL Server are popular database systems, but as we continue to move into big data and unstructured data, you may consider learning new query languages to make sure you stay competitive in the job market. SQL is a well-known as the easiest programming language to learn because it has the fewest commands. I think it has only around 100 commands. And in an attempt to continue using SQL with Hadoop, which is a common unstructured database platform, Apache Hive was created to use as a SQL on Hadoop solution. But in the data science world, you might want to learn something like Scala, which is pretty popular right now. Your book also goes through ways that you can use R to interface with a MySQL database in order to query from a database and then perform analysis on that data in R. That's not going to be the main focus of this class, but it is in your book if you think you might be able to use it. So, the next step in the data mining process is the pre-processing of data. And this is generally the one that takes the longest because data is almost never in a clean state that we can directly begin our analysis on. So the definition of what tidy data is on the slide, so I won't read over it, but there's a couple of packages that you can use in R that will help kind of streamline the cleaning process. One of those is called the tidyr package, and the lab that I connected, if you go that route, uses tidyverse, and it'll help clean the data for you. Yeah, so tidyr is an R package that can assist in cleaning the data, and it puts it in a standard form that you can then feed into algorithms to do your analysis. So after our data is clean and ready to analyze, we can go through the process of selecting which variables or features. So in your assignment with the Lending Club data, like I said earlier, there's I think 157 variables, and I want you to select 4 variables that might help predict whether a loan is going to default. Now you can use wrapper methods or filter methods. Filter methods generally work better if you do not have a good idea of which variables might be useful in the analysis. However, wrapper methods may be more useful if you have prior knowledge and a good idea of what variables to use. Ways we can rank variables might be whether they are statistically significant, which allows us to remove non-significant variables. We can also look at parameter estimates or coefficients and pick the variables with higher coefficients as they'll have more predictive power. Your book kind of separates this out, but I might look at a correlation table first and try to see which variables are highly correlated. And if 2 variables are highly correlated, then they're going to be explaining the same amount of variance, so you may want to choose one or the other. And that's another way you can kind of select your variables. Overall, I think variable selection and exploratory data analysis kind of need to be done simultaneously to make sure you do not drop variables that would actually be good predictors. So the next stage in the data mining process, after we have our clean data set and we kind of have an idea of what variables we're going to use, is the modeling stage. exploratory data analysis, this is when we're going to use, this is where we want to do our basic like descriptive statistics, like we talked about before, mean, median, correlation, and might also want to look at visual summaries, in particular maybe scatter plots, and find if we use a scatter plot and find that there are clear clusters of data, then a clustering algorithm might be useful. So as we're doing this process, we might start to see which algorithms would be best to use. And we're going to talk about clustering later in the class, and I think the last week. But the difficulty with visualizations occurring is as we move into higher dimensional spaces, or when we have more than 3 independent variables, then it becomes hard to visualize that data in a meaningful way. So this is a small tidbit about clustering, but we will cover this more in detail in week 8. Basically, we want to see if we can segment the data based on its dissimilarity. So we'll say this particular group is different than this group, and that'll be our first way that we can cluster it. And then you can do this hierarchically and continue breaking down the clusters of data. It's particularly useful in marketing and market segmentation. So the main focus of this class is going to be on predictive analytics, methods, and algorithms. We can break this into 2 categories: the classification algorithms and regression algorithms. Few examples of classification algorithms are neural networks, support vector machines, logistic regression, which can kind of fall into both categories, but I think logistic regression is better as a classifier than it is as a regression algorithm. We're just trying to classify some data and put it into a bucket, basically. Like if you think about your assignment, you're trying to predict whether a loan is going to default or it's going to be paid off. So is that data point going to fall into the paid off bucket or the default bucket? Or that's how we're going to classify it. But regression algorithms want to predict an exact value, such as taking a set of variables about the housing market to predict the highest price you could sell your house for. Examples of these are linear regression, stepwise regression, polynomial regression, etc. So after you have selected a model, you then need to evaluate the quality of that model. Last semester we talked about the confusion matrix to define our predictive power. So that's where we looked at the number of false positives, the number of false negatives, the number of true positives, and the number of true negatives. Then we can calculate our sensitivity and specificity of our model. So another set of models we look at are tree-based models. These are hierarchical models where we are trying to classify a set of data, or with regression trees, we're trying to predict a value. But basically, the algorithm learns how to separate the data. In a supervised version of a tree-based model, we tell the model where and how to split the data at each branch. But in unsupervised versions of the model, we let the algorithm pick the best splitting mechanism. If we have a multitude of decision trees, then we call this a random forest algorithm. An example would be if you worked for a marketing company and you were trying to determine what a single customer might want to buy, then this would be a single decision tree. But if you wanted to determine what a single customer might, or find out what a group of customers would buy, then each person would be a tree, and combined you would create a random forest algorithm. We do random forest algorithms in assignment 4, so the last couple of weeks of this class will work on that algorithm.
When do you know if you want to use a train, or what did you say? Not train.
Supervised or unsupervised?
Yeah, supervised. When do you know which one you want to use?
Supervised you generally do if you know what the goals of your analysis. When you do unsupervised, it's usually more like kind of exploratory research. you don't know what to expect, so you just kind of see what emerges when you run the algorithm. So as it decides how to separate the data in the tree, then that's kind of what you're looking for, is how is this algorithm going to separate it? How did it decide? Does that make sense?
Yeah. So which one is a more powerful algorithm?
They're both about the same. Like I said, it just depends on what your goals for the analysis are.
Oh, okay, okay.
So, I mean, you may try to run them both just to see what happens. So maybe you have an idea of what you think, how this data should be split up and classified, but you let the unsupervised version see if it can do a better job. So when you go to evaluate, you can determine, well, this is what I thought, and this is what artificial intelligence or machine learning algorithms, I mean, they're both machine learning algorithms, but just the unsupervised version may be able to outperform what your initial thoughts were. But it really depends. So another classification model is called a support vector machine. The goal of a support vector machine is to split or classify a set of data by using a line or a hyperplane in higher dimensions. So anything above that line is classified into one group, and anything below that line is in the other group. So we're going to do this in assignment 2. So when we get to that one, I'll talk a little bit more about support vector machines. So after we've modeled our data, the next thing we want to do is to evaluate the predictive power of our models. Sometimes we'll want to compare the different ones. So let's say we ran a random forest and a support vector machine and a logistic regression model. This is where we want to compare all those models to see which one actually does the best predictive job. We can do this with a few different techniques, such as cross-validation, bootstrapping, and we're going to use the use of train and test sets. Cross-validation is a very common method of testing predictive power. Bootstrapping is used more in algorithms that I don't think we're going to cover in this class, but bootstrapping involves random sampling with replacement and is used sometimes if we have smaller data sets and limited test train capability. So after we think we have a good model, then we want to deploy it in the business setting that it was designed for. So the last step is to deploy your model, correctly communicate your results to the key stakeholders that you interviewed in the first step. And if you think about it, if you reflect on our last semester, this is why I asked you to do that final presentation. And in essence, you've already gone through the entire data mining process in DSIM 603. So I wanted to talk a little bit about the assignments as a kind of quick review. This week's assignment asked you to go through the data mining process on a new set of data, the Lending Club data. Develop a regression model with 4 variables. Then, all of the other assignments still use that same data. In assignment 2, you will use the same data but develop a support vector machine, and then explain the differences between those 2 models. In assignment 3, you will use the same data again, except you're going to develop a naive Bayes model, then compare and contrast the 3 models. And in the last assignment, you will use the same data, form a random forest, and then compare and contrast the 4 models. So, does everybody understand kind of the goal of this class and the goals of the assignments? Is everybody all right? That's kind of what I planned to do. Good? Yeah, that's cool. Just wanted to give kind of of what I was pulling out of chapter 3 for this talk, and I think next live session we'll actually get into